next up is arguably the most useful thing we can actually do by using the alpha position of a carbonyl group, and that is to put an alkyl group there. So we're looking at forming a new carbon-to-carbon bond here, and the first step, removing one of these hydrogens, gives us a very good nucleophile. So that is what we're having here. Our enolate is a very good nucleophile, very carefully chosen base here so that we get basically 100% conversion to the enolate. And then this is a straight up SN2. We've got a very good nucleophile. We'll have an alkyl group with a leaving group, usually a bromide, sometimes an iodide, and we get something very specific happening. But let's remember something here. We do have limitations on the SN2 reaction. One, can't be used with an sp2 carbon, which means we can't put an alkene or an alkyne there directly, or an aromatic ring there directly by this process. Two, the SN2 reaction absolutely does not work if you have a tertiary carbon attached to your leaving group. So if I wanted to put a tertiary group here, I'm out of luck, at least by this method. I'd have to go by a different method, which would be a lot less simplistic. Not a big problem for us most of the time, but in the course of working within chemistry, nature and the need to fool it as part of pharmaceutical design does tend to throw us some odd curveballs, so we do have to have backup plans occasionally. But most of the time, this works just fine. Okay, so again, can't use that. Secondary works, it's just slow. And you have to be careful with conditions, otherwise elimination becomes a problem. We haven't talked about the aldol yet. I'm doing this in slightly different order. But the point is we need quantitative enolate, which means we need a strong base, period. No option. We can't go away with anything that has a potential equilibrium going on. And if we have unsymmetrical ketones, the amount of base and the conditions are going to control which exact enolate will form. That's the important part here, in that if we have unsymmetrical enolate, unsymmetrical ketone, so I'm looking at deprotonation either here or here. Well, we can force one or the other, at least we can force this one. The bigger the base, the harder it's going to be for it to get here. So we can control the one on the left pretty easily. That gives us the structure on the right. That gives us what we call the kinetic enolate. It's a less stable alkene, but it's an easier hydrogen to get to. Kinetics, remember, is about the easy way out, lower activation energy. Much like many other contexts in life, the easy way out is not always the best way out. So this doesn't necessarily give us the most stable enolate or the most stable product when it's over. If we put this under slightly different conditions where we can get to that other hydrogen, and we'll talk about those conditions are in a moment, then we get to a more substituted enolate, a more substituted alkene, and eventually a more substituted a substitution at the originally more substituted side of the ketone. So here's the easy way out problem. This is the kinetic version. Do things the easy way, doesn't require much work, but it doesn't get you stability. This is the less substituted alkene, it's less stable. To get the better energetic outcome, it's going to require higher activation energy. So this is what we're having to put in to get there, to get the thermodynamic one, as opposed to this, which is my energy of activation for the kinetic control enolate. But look at the payoff. If we had these written out, this is delta G for the kinetic, very small payoff. Is delta G for the thermodynamic, much larger payoff. But we're going to tend to have to work a little harder to get to it because it's going to require equilibration. Okay, so how are we going to get to equilibration? Like I said, getting the kinetic version is easy. Bulk up the base. A big base is not going to be able to fit into a tight spot to get a more sterically hindered hydrogen. This is like trying to park a truck in a motorcycle spot. It just isn't going to work. You're going to have to go and find a spot you can get to easily. Well, that's as easy as it gets. The other case, well, first of all, we're going to go with a smaller base. This is kind of this, although that is oversimplifying it. It does have bigger structure than that because of aggregation and how the metal handles it. But the point is, it's not nearly as big as this behemoth over here. Remember, this is the diisopropyl amide. So even with a little bit of extra stuff hanging on this, like solvent and, we're not going to have anything close to the same bulk. So this is definitely not going to have as big of a preference for one over the other. It's still going to prefer the easy one. Now there's a problem there. If the easy one is still preferable, then how are we ever getting the more stable one to dominate here? We're going to have to undergo equilibrium. Now, that is a lot more messy mechanistically, and your book basically doesn't touch it. So that's what you have me for. How do we get to that point? Here's what happens. We're going to have something unsymmetrical. We'll stick with the same example because then you have it as an explanation along with what's in their diagram. So our first step is still going to be the deprotonation. So we're going to have sodium hydride. And we're going to end up with some ratio of this to this. That ratio is going to be still favorable towards the easy one. But because we let this equilibrate, what we're going to get is we're still going to have some of this present. So this very importantly has to be reversible for us to ever get here. So the idea is this is lower in energy. If we go back to their energy diagram, remember, this was a diagram like this where the check-marked one is way down here. So this process, going back up and over to reform the original ketone, is going to be slower. So remember, this is our energy of activation for the reverse process from the structure on the right. It's going to be much slower than this one to go backwards. So this is going to be comparatively fast. This is going to be comparatively slow. The forward rates are what they are. We're not going to alter those unless we change the temperature. But the point is, what we're going to see over time is, we'll make up the numbers here. Don't quote me on the numbers, but let's say we started off statistical. Let's say we started out immediately. If I stopped this reaction immediately, I would have had something like this. But over time passing, we end up getting better because more and more of the kinetically controlled one is reversing and then getting sent forward in that 1-to-1 ratio. And eventually we'll get to some ratio that's based off of the actual preferences for the delta G values. That's not going to be 100 to 0. That's almost unheard of. It's not impossible, but it still will be very favorable because there's a big difference between the alkene stability. If we look at the resonance structures for those, which I didn't draw here just to make it a little simpler, but if we look at them, we're looking at this versus this. These are our enolate stabilities. So this is a much more substituted alkene. This is a tetra-substituted alkene. In alkene terms, that's as good as it gets. This, less so. This is tri-substituted and less alkyl groups. So remember, the alkyl group is going to have hyperconjugation if there are any hydrogens on the carbon that's directly attached to it. So we're talking about a much better stabilized system, hence the big difference in energy that you see here. So that's the question. Now, basically, the one thing they don't touch is that we do need some of this left around. And so one way to blow this out is, and make sure we don't equilibrate, is to use a stronger base, second, a larger base, and third, lower temperatures, so that equilibration can't get over either of the reverse humps to actually go backwards. If I want equilibration to happen, so if I don't want equilibration, or let's say limited, what I want is, one, a stronger base, 2, I want lower temps, so there's less energy in the system. And 3, I need the ketone present to be able to do the equilibration. There has to be some of it left. So if I want to make sure that I can't do equilibration at all, I want to use excess base. Therefore, very quickly, no remaining ketone. That has to be there for equilibration to happen. If it isn't there, well, we don't have the possibility of equilibration. So, if I want equilibration to happen, then I want to go against all of that. I want a slightly weaker base. And remember, this is within reason. I still want most of it deprotonated. I don't want 5% of the enolate. I still want a very large quantity of it. So this has to be sort of, we don't want weak, but weaker. So we have a little bit more time to work. 2, we're probably going to talk about higher temps. LDA is usually used between -80 and probably about -20. Here we're talking about, if I go back to the actual slide, we're talking about room temp, or in that neighborhood. So that's a lot more energy in the system, which means getting back up and over those activation energies is easier, is more likely. And 3, we'll sometimes use a slight deficiency of the base. What I mean by that is, instead of using, like for excess, I would say I want 5% extra. So we describe that as saying 1.05 equivalents. That's how we write it. Is that means I have an extra 5% mole-wise of the base. So therefore, I'm basically guaranteeing there's going to be no ketone left. A slight deficiency, a slight deficit. So here I'd probably use something like 0.95 equivalents. A little bit less. What that means is that I'm always going to have 5% of the ketone remaining at all points. It's a little bit wasteful. We do lose 5% off the top of our yield if we do this, but the point is, it gives us a guaranteed way to equilibrate it, because this needs to be there for equilibration to happen. Without it, we get no equilibration. So we're toning down the speed to make sure some of it's there. We're making sure there's enough energy for the reversal to happen, but we also need to make sure absolutely that the ketone is present in some amount. So we'll sometimes take the base amount down because of that. Your book doesn't touch this, but in case you see it in another context, specifically it comes up in biochemistry a lot, the excess reagent versus deficient reagent. It can change what happens dramatically, because you have leftover unreacted starting material if you don't have enough of what it's reacting with. That's a very important point in a lot of contexts. I'm a little disappointed your book didn't touch that. All right, so now, one way that we can use this a little bit more easily, because sometimes ketone deprotonation is not trivial. It works relatively well depending on the conditions, but it's not the simplest reaction in the world. This is not laser fast that we can always get things done as quickly as we'd like. One way we can get around that is we double it up a bit. And here's what I mean by that. We use a case where we have 2 carbonyl groups. Now, your first inclination here is going to be, well, but that gives me extra stuff. If I wanted to just alkylate next to an ester, which is very difficult on its own, or if I wanted to just alkylate next to a ketone, why do I want an extra group hanging off the side of it? The reason is it's an activating group that we can then dispose of. It's something we can get rid of. So that way we get a reaction that's easier to do, and the group that we use to speed it up is disposable at the end, and we get rid of it. So first version of that is called malonic ester synthesis, and basically it allows us to make substituted acids. If I try to do this directly from an ester, it's very difficult to do. So this doesn't work very well. I'm going to have to basically go through some sort of activation to get this to occur, because this is just not active enough. The way we do that is we put a second ester in on the other side. So that's what you're seeing at the bottom here is a diester called a diethylmalonate or a malonic ester. It doesn't have to be ethyl groups, but that's typically very common. When it comes to esters, our base basically has to match the ester. We can get away with it not matching it in this case, but generally we choose the ester to match the base, so ethyl and ethyl. We get an enolate that's stabilized. So this is resonating throughout in both directions into both carbonyl groups. Stabilized in that it's easy to form, it doesn't mean it doesn't do anything. All right, so then we have our traditional SN2. Again, same limits as before. The SN2 reaction does not allow us to use alkenes as our leaving group. It does not allow us to use aromatic rings as our leaving group. It doesn't allow us to use tertiary carbons attached to that leaving group. So we do have limitations here. It's good to keep those in mind. All right. Afterwards, we do the ester hydrolysis that we've seen back in the carboxylic acid derivatives chapter. So we end up with a diacid. Now, this needs to go. I only wanted one of them, so one of them's got to go. If you look at it closely, you can kind of see what's probably going to happen here is that's just carbon dioxide with a hydrogen on it. So if I basically kind of don't look at that H for a minute and picture somehow this happening and this bond breaking, that's carbon dioxide. So I can kind of see without thinking too much about it what might happen. Question is, how does it actually work? All it requires is additional time, basically. Once it's hydrolyzed, I just have to let it sit there, heat it up a little bit. It's not particularly difficult to do. It requires a little bit of a different conformation, though. Specifically, this is going to rotate 180 degrees because I need this to be hydrogen bonding to this. So that's what you're seeing down here, is that they've rotated that 180 degrees. This is actually hydrogen bonding to begin with, but the point is it's almost bonded to begin with, so that the actual formation of a bond there is not particularly difficult to see. Once we get that off there, we have a driving force to form a second bond to the carbon. So if we had the original carbon where it was, like this piece here, it would be right here, and that bond that just formed is that. The other one was already double bonded, so this is the arrow that forms that bond. It's the loss of this hydrogen as the other bond to the oxygen forms to it. And then what we have, if you look at it, is an enolate. So an enol, sorry, which then tautomerizes to the carbonyl, which in this case is a carboxylic acid, with our shiny new R group attached that we could not have done directly in a very easy fashion. So this is one good way to make substituted carboxylic acids. We can, they don't mention it in this particular slide, but we could do it twice. If we go back, we could take this and do it again. Do the whole process a second time and get a second one there, so we can make di-substituted carboxylic acids if we need to by this method. So, oh sorry, they did mention it. I hate PowerPoint. So, yes, we can do it again. All right. What about a ketone? That's what we were most of the time. Ketones work, but they do present some problems at times. So we have a similar process. We have a disposable ester that's going to end up being a carboxylic acid and then getting converted to carbon dioxide. We have a ketone, which is active on its own, but now is much, much more acidic than it would have been if it were just acetone. And we get no mixtures out of this. We have a very active site and a much, much weaker one here. So we don't have anything to worry about there in terms of getting substitution at the wrong spot. And as before, we could do this twice before we do the decarboxylation to give us a di-substituted ketone, helping us avoid some of the mixture problems that we would have had otherwise. These acetoacetic ester, which is what this is acetoacetic acid ethyl ester, is readily available, so we can buy it. It's relatively cheap, and we can go forward with it.